Welcome to the Research Highlights video series. These videos are intended to provide a summary of some of the research being conducted by members of the Hopkins Group at the University of Waterloo. This video will discuss some of our recent work on rhodium sulfide clusters. For a more detailed discussion about the properties of rhodium and rhodium sulfide clusters, please read our recent article which appeared in the June 2014 issue of the Journal of Physical Chemistry A. The mission of this study was to see how sulfur impurities affect the structures and properties of rhodium clusters. This is a particularly pertinent question to ask because rhodium is a major constituent of the automobile three-way catalytic converter, and sulfur, which exists as an impurity in fuels, is a known catalyst poison. To identify likely candidate geometries for the cluster structures, we employed the basin hopping search algorithm. Basin hopping essentially employs a random walk across the cluster potential energy landscape, and it identifies cluster structures by projecting the random geometries onto stable local minima. This transforms the potential energy surface into a set of interlocking staircases where each unique plateau is associated with a unique structural isomer. By introducing a thermal energy control, our search targets the global minimum or lowest energy structure, and we can introduce user-defined criteria to help speed up the search. Having identified a test set of structures, we can carry these forward for calculations at the density functional level of theory. This yields more accurate predictions of cluster structures and properties. Immediately, we see that sulfur prefers high coordination adsorption sites, actually adopting the same position that another rhodium atom would have. We also find that rhodium sulfide clusters exhibit ionization energies and electron affinities that are very similar to those of the analogous bare rhodium clusters. This too suggests that sulfur is behaving like rhodium, and that rhodium sulfide clusters will behave as if they are metallic clusters. To determine the magnetic properties of our clusters, we must calculate the electron spin density. In doing so, we find that both the bare and sulfur-decorated rhodium clusters adopt highly open-shell electronic configurations. For example, the ground state of the rhodium-8 sulfide cation has 13 unpaired electrons. Thus we see that while bulk rhodium metal is non-magnetic, rhodium clusters are superparamagnetic. Since the magnetic moments of the rhodium sulfide clusters parallel those of the bare rhodium cluster, it looks again as if sulfur is behaving like a rhodium atom in these species. Cluster stability is often gauged by the size of the HOMO-LUMO gap. Oftentimes, people will assume Koopman's theorem and estimate gap size as the difference between ionization energy and electron affinity. Such an approach is not valid here, owing to the fact that cluster geometry often changes with charge state. We also run into a problem when trying to calculate the HOMO-LUMO gap with density functional theory, because the gap size is found to vary dramatically with choice of functional. Instead, we can assess stability by calculating the dissociation energies of the various cluster fragmentation thresholds. Here we see that upon fragmenting, bare rhodium clusters prefer to eject a single rhodium atom. Similarly, and at similar dissociation energies, rhodium sulfide clusters prefer to eject a single rhodium atom. This behavior is commonly observed for metallic clusters. We see that removing sulfur from these clusters is a high-energy process, and it is likely to come at the expense of a rhodium atom. Natural bonding orbital analysis shows us why this is the case. We find that the sulfur bonding is stabilized by donation of electron density from the sulfur 3p lone pairs to vacant orbitals on the rhodium clusters. Back donation then occurs from the rhodium cluster into a valent sulfur 3d orbital. It is important to validate theoretical predictions with experiment. Our predictions could be tested by measuring cluster magnetic moments, dissociation energies, ionization or detachment energies, or electronic and vibrational spectra. The groundwork for all of these has been laid. Now it's time for us to do some experimenting. For more information about Hopkins Group members and the research that we conduct, please visit the group website, which is hosted by the University of Waterloo Department of Chemistry. Thank you for your time and interest in our work. See you next time.